I previously introduced the filtration system for my 3D printer, but that's just one part of the overall Tophat system. Today I'm going to show you the other two systems I've integrated, and how they work together. If you've noticed the extra holes on the top panel, those are for the part cooling fan and the exhaust fan. Hi, welcome to Slow Engineering, I'm David. Let's start with the part cooling fan. Instead of mounting it directly onto the tool head, I separated the part cooling system entirely. This simplifies the printhead design and avoids the need to change the cooling setup every time the tool head changes. So now the part cooling fan is located at the top of the printer. From there, it pulls in the warm air inside the enclosures and directs it down to the printhead. This is especially useful for materials that don't tolerate cold air well. At the same time, the design still supports strong airflow for materials like PLA that need aggressive cooling, since the fan speed can be increased when needed. From this setup, I'm using a 70 floaty blower fan. It connects a hose from the top and channels the airflow to the printhead. To keep the wiring neat and efficient, I place both the fan driver and the adapter board directly on top of the fan housing. The fan cover has more cutouts than the top panel, so I can easily adjust layout later if needed. The control board is designed to work with the PWM signal headers from the 3D printer's mainboard. There's a 47K ohms resistor acting as a pull-down to stabilize the PWM signal. Then two MOSFETs step up the signal to 5 volts. Which is what the fan driver requires. I used the MOSFETs to isolate the signal coming from the mainboard. That's because the fan driver's control pin shares the same ground as its power ground, which can conflict with the signal ground from the printer's mainboard. If I connected the signal pin directly without isolations or a pull-down resistor, the current would flow straight to the ground, and the signal would vanish, making the fan driver think there's nothing there. The pull-down resistor stabilizes the PWM signal, and the MOSFETs cleanly shift it to a proper 5V level that the fan driver can read. Even though this setup inverts the signal, it works fine, just that the firmware node is inverted. The key here is to keep the fan driver's logic and power grounds aligned while protecting the mainboard signal line. Now let's move on to the exhaust fan. The original 114mm snug fan already did a good job, but I wanted to improve the airtightness of the system. So I added a valve to seal the enclosure during printing. This helps ensure better air filtrations and reduce leakage. The valve I'm using is a 24V solenoid model with 3 pins, one for opening, one for closing, and a shared ground. While testing, I noticed that the voltage needs to be held until the valve completes its motion. If the voltage drops too early during opening or closing, the valve might not finish the cycle as expected. For example, if the opening voltage drops midway and then the closing signal is sent, the valve still opens fully before starting to close. But if you interrupt closing and then apply the opening signal, the valve jumps straight to opening again. I think this is a safety mechanism to make sure that the valve won't turn over and break the sealing mechanism. To manage this, I designed another adapter board specifically for this valve. It uses two PWM signal headers from the mainboard, one to open and one to close. The circuit is simpler than the one used for the blower fan since it only needs on-off control. I use an N MOSFET and a P MOSFET to toggle the valve, along with diodes to block any reverse current that could damage the system. This board also supports direct wiring from the mainboard's PWM signal pins, which makes firmware setup more straightforward. To improve airflow, I relocated the Tophat fan to the outside of the enclosure. This lets air move smoothly through the buffer space inside. I designed a new housing that integrates the fan with the valve and includes bayonet groups that match the flexible tubing I'm using. The fan connects to the filtration system's controller and then to the printer's mainboard, enabling full high-frequency PWM control, just like a standard PC fan. The whole setup for the fan driver is now stable, safe, and fully controllable through the mainboard. So, with airflow and cooling out of the way, there's just one more thing I want to touch on: lighting. I'm planning to install LED strips along the outer edge of the enclosure, this time on the outside rather than inside as before. The old setup caused the strips to fade quickly due to heat buildup. To address this, I'm now mounting the strips on thin aluminum bars for passive cooling and improved heat dissipation. To support the bars, I modified the existing corner fixings, the ones that originally held the top panel, so they now serve a dual purpose. My first idea was to shine the light straight down, parallel to the top panel. But then I saw, I'm using 3D printing parts. Why not tilt the bar slightly and angle the light toward the center? So I redesigned both the fixings and the bar supports to create angled mounts. This not only focuses the lighting where it's most useful, but also helps reduce glare for the user. The LED strips I'm using are COB type, which provides smooth and even light diffusion. I also left internal space in the corner design for wiring routering and added exit holes for clean cable management. By wiring both ends of each strip, I can prevent voltage drop issues that usually cause uneven brightness across the lens. Each aluminum bar has a small hole drilled near the end, which lines up with the bridge support underneath. To install it, I insert the bar into the groove first, then align the holes and secure it in place. This simple method maintains the bar's stability while keeping the overall structure clean and modular. What do you think about these updates? Let me know your thoughts. I always appreciate feedback. Thanks for watching, and as always, keep moving forward.